Hi everyone. Today I'm going to solve all the questions that were asked from you in quiz number 3. The topic is common collector. So this is the first circuit that was given to you for question number 1 and question number 2. The first question asks, what is our in total here? So looking at the circuit, we see that this is a common collector amplifier because the input is at the base, the output is at the emitter, and if you consider the AC voltage, the AC analysis here, if you ground this power supply, which we do in AC analysis, then the collector becomes grounded, and that's the definition of the common collector amplifier. Okay, so I drew the circuit here. Again, R1 is 10 kilo ohm, R2 is 4.7 kilo ohm, and RE is 1 kilo ohm. Beta AC and beta DC are also mentioned here. Okay, in order to solve for R in total, let's start by redrawing this circuit in AC. So in AC, we do two things. One is that we short circuit the capacitors. The second thing, as I mentioned before, is that we ground the power supply, the DC power supplies. Okay, if we do that and redraw this circuit, this capacitor becomes short circuit, acts like a wire, and connects V in directly to the base here. Then we have at the base, we are at the base now. We have R2, which goes from base to the ground. So we can draw that. R2 to the ground. This is 4.7 kilo ohm. Then if we ground this power supply here, we ground it, make it 0. Then it is as if R1 goes from the base to the ground as well. So we can just make it parallel to R2. So R1 is 10 kilo ohm. What else we have? So we are done with the base now. Now we should put the equivalent circuit of this transistor. So a transistor in AC is modeled by a dependent current supply that goes from the collector to the base, then from the base to the emitter by R prime E. R prime E is 25 millivolt over IE. This is the DC value of the emitter current. Okay, so let's do that. Let's connect the current source here, and this current source is actually beta AC multiplied by IB equal to IC or almost IE. So now we have R prime E here. Now we are at the emitter, so we are here. So next thing we have to draw is RE. RE, which is 1 kilo ohm. Now let's finish the terminals here. IE is here as well. This is the amount of this current is IE. Now we are at the collector. If we ground this power supply here, now the collector will be grounded. So we connect it to the ground. And V out is at the emitter. So not here, actually here. This is V out. Right? Okay. Now in order to find our in total here, we can see that our in total is R2 in parallel with R1 in parallel with another resistor that we call R in base. R in base is whatever resistor we see from the base of the transistor onward. Okay, so let's write that down. Our in total is R1 in parallel with R2 in parallel with R in base. So R1 and R2 are given through the circuit. What we have to calculate is R in base. So let's calculate R in base here. Now, if you don't remember this, what R in base is, you can do, you calculate it from the beginning, or if you remember, it's beta AC multiplied by R prime E plus RE. So whatever resistor we see at the emitter, which is the series of these two, so they will be added, and since we are looking through the base, it will be multiplied by beta. If you don't remember this, you can just use basic circuit theory and say R in base is basically through Ohm's law, it's going to be VB over IB, basically. The voltage at this point, which is the voltage at the base, to the current that goes through the base, to the current that goes through this node here, which is IB. Remember, this IE is here, IB is here. Okay, so since IB is small, all of this current that you see here, IE, is going to go through this resistor. And VB, which is the voltage over this path, all of this path is going to be, again, Ohm's law, is going to be IE multiplied by R prime E plus RE. This is over IB. Since IE is almost beta AC IB, we can replace it with that, RE. Then we put IB here. So IB and IB cancelled. So you see that beta AC becomes R prime E plus RE. So this is just a proof. If you remember, you don't have to write this. This is just a proof of why R in base becomes beta AC multiplied by R prime E plus RE. So this is just a proof. You don't have to repeat this in your exam. But now let's go back here and write this down. I'm going to move the video so you can follow it. Okay, so R in base becomes beta AC, which was given to us here, 100, multiplied by R prime E, which we don't know yet, plus 1 kilo. R prime E is usually small, so you can either calculate it or just say it's small compared to 1 kilo ohm and ignore it. I'm going to ignore it for now and then also repeat it if we didn't ignore it. So for now, let's just assume this is almost 0. So 100 multiplied by 1 kilo ohm becomes 100 kilo ohm. Okay? Then what we have to do for R in total is that R in total becomes R1, which is 10K, in parallel with 4.7K, in parallel with 100 kilo. For this, you would get almost 3.1 kilo. If you just parallelize the 4.7 and 10K, you almost get 3.2. So I saw some answers that did this. I gave you some marks, but when I see 3.2 kilo ohm, I can see that you ignored R in base here. And although it has a small effect, it is important that you know that you should consider it. Okay, actually, later I'm going to calculate R prime E for question number 2. So for now, let's just consider it to be 0. So this is the answer for question number 1. Now, let's go and solve this for question number 2. So again, for question number 2, we have the same circuit. So I'm going to draw it here quickly. R1 is 10 kilo ohm, R2 4.7 kilo ohm. We have V in here, RE 1 kilo ohm, V out is here, and then we have VCC 5.5 volt. Okay, beta AC is 100, beta DC is 90. How do we solve this for DC? So first we have to see how this looks like for DC. In DC, what we do one thing, and that's open the capacitors. Okay, if we do that, I think, oh, better. If we do that, then that means that the input signal V in, if we open this, is going to be disconnected. And the circuit that remains is only this part. So you've seen this a couple of times. This is a voltage divider biased amplifier. Now, in order to find what is the DC value of V out, you can see that V out is actually equal to the V emitter because it's right at the emitter. And we know that for an NPN transistor, V out or VE is equal to VB minus 0.7 volt, right? And this is VB. So if I find VB, then I can find V out. And VB here, as I mentioned, you can use voltage divider. You can consider this to be open because IB is very small. So you can say it's 4.7 or R2 over R plus 1 R2 multiplied by VCC, which is going to be 4.7 kilo over 10 kilo plus 4.7 kilo multiplied by 5.5 volt. So if you calculate this, you get, let me just calculate this very quickly. This becomes 1.7585 volt. So then V out in DC becomes VB minus, which is VB minus 0.7 volt becomes 1.7585 minus 0.7 volt becomes 1.0585 or 1.06 volt almost. So if you got this number or something close to it, you're good. Okay, this is question 2. Now we are done with this circuit. Now we are going to move on to question number 3. So let me just move this. So question number 3. In question number 3, you were actually given a Darlington pair, which is another type of common collector amplifier. So we studied this pair in our lecture number 10, and if you remember, the application of this type of amplifier was that it would help you to increase beta. So this is Q1, this is Q2. Beta DC1 is equal to beta AC1, 150. Beta DC2 is equal to beta AC2, 100. And then we have 10 microfarad Vn. So this is IE2. the emitter current of Q2, and it is beta, at least in DC, it's beta DC2, the beta of this transistor, multiplied by the current that goes to the base of this transistor, IB2. So let me write that down again. IE2 is beta DC2 of IB2. Now, if you look, IB2 is exactly the current that comes out of the emitter of transistor 1. So IB2 is equal to IE1, the emitter of transistor 1. So I call it IE1. So this becomes beta DC2 multiplied by IE1. Now again, IE1 is beta times the current that goes through the transistor 1. But you have to multiply it by the beta of transistor 1, which is beta DC1. Then IB1. So you see, now if you look at this as just one transistor, the two pair together, if you just look at it as a black box, it gets IB1 and it outputs IE2. And we have some IC here as well, IC1 and IC2 here as well. But when we say the effective or the beta AC of this transistor, what you can do, either say, okay, it's going to be beta DC2 multiplied by beta DC1. Because now, if you divide IE2 over IB1, the output current to the input current, the output current to the input, it's going to be beta DC2 multiplied by beta DC1, which is going to be 100 multiplied by 150, which is going to be 15,000. If you want it to be very quite exact and use the fact that IE is actually beta plus 1 times of IB, then you can also say that this is approximate. IE2 over IB1, it's going to be beta DC2 plus 1 multiplied by beta DC1 plus 1. It's going to be 1001, 151 multiplied together, and it's going to be 15,251. So both of these answers are correct. Oh, sorry, I didn't show you here. So yeah, if you use the exact value and do it this way, you get 15,251, which both of them are very close compared to that. The order of magnitude is actually quite large, so 251 and 0 are close to each other. Okay, so you get full marks if you wrote any of these two values. Now let's go at question 4 and question 5, which a lot of people had problem with. Okay, so for question 4 and 5, again we have the Darlington pair. So we have Q2, then RE, 1.5 kilo ohm, Q1, then this is 33 kilo ohm, R2, 22 kilo ohm. We have V in, VCC, which is 10 volt. Beta AC1 is equal to beta DC1, 150, beta AC2, beta DC2, 100. Okay. So in question 4 and question 5, you are asked to calculate R prime E for Q1 and Q2. First is R prime E for Q1. So if you wrote the same number for R prime E, Q1 and Q2, that's a big no-no. So we don't want to do that, because obviously, or we should start actually by saying that R prime E is 25 millivolt over IE. Which emitter current? When we are calculating for transistor Q1, we should put the emitter current of that goes here. So now you know that this is IE1 here is equal to the current that goes through the base, IB2. This is IE2, right? Okay. So what we need to do actually then is to calculate IE1. So let's do that. Let's calculate IE1. So the easiest way would be to calculate actually IE2 first and then move to IE1. Then here to the base, IB1. So just as we did it before, first thing we do in DC, because this is a DC value, we just open this one. So we say that we have to find what is VB here. VB based on voltage division is 22K, this resistor, to the total of these two resistors, which is 22K plus 33K multiplied by 10 volt. So it's going to be 22 over 55. It's going to be 4 volt. Okay. Now, the voltage here, let's call this VE1 or VB2, doesn't matter, is equal to, VE1, which is equal to the voltage of the base of the second transistor, equal to VB2, is equal to VB minus 0.7 volt. So it's going to be 3.3 volt. Good. Now we do this again. We move from this point to here. Now we say VE2 is going to be VB2 minus 0.7 volt. The voltage here, VE2, is going to be minus 0.7 volt below this amount. So it's going to be 3.3 volt minus 0.7 volt, it's going to be 2.6 volt. Now, based on Ohm's law, IE2 is going to be VE2 over RE. This is not RE, which is 2.6 volt over 1.5 kilo ohm. So 2.6 over 1.5, it's going to be 17 milliamp. Now, if we want to